Okay, so sorry about that. My recording software froze on me. So I'll try to pick up sort of where I left off here. So we're discussing that here we have the heat of fusion at this plateau. So if you take the difference between the heat at C and the heat at B, in other words, we're talking about heat in terms of Q, okay, or delta H. Okay, so the difference between point C and B, or the delta there, would be the heat of fusion. And then the difference between points E and D, that would be our heat of fusion for vaporization. Okay, so the next thing to know here would be the phase changes. Okay, so I could ask you, for instance, to label the different phases. So what phase would, in other words, what phase would matter? What phase of matter would this sample be in from A to B, or what phase would it be in from C to D? Okay, so make sure you can label those, and just based on understanding that those plateaus indicate phase changes. Okay, so I could ask you, for instance, what is the normal melting point of this substance, or what is the normal boiling point of this substance? Okay, something like that. Okay, so the next topic will be vapor pressure. But first, let's take a look at sort of a kinetic energy diagram here. So this is the distribution of thermal energy. So on our y-axis, we have the fraction of molecules, and then on our x, we have the kinetic energy. And the first thing we should look at is the blue line and the red line. Okay, so with the blue line, this represents the sample being at a lower temperature. And what we see is that at a lower temperature, more of the molecules have less energy. Okay, so more of the molecules are sort of in this region. Okay, compared to at a higher temperature, we shift this curve to the right and we flatten it out a little bit. Okay, so at higher temperature, more of the molecules have higher kinetic energy. Okay, so lower temperature, more of the molecules have lower kinetic energy, and at a higher temperature, more of the molecules have higher kinetic energy. And if we take a look at one particular point on this curve, okay, we take a look at how much kinetic energy each of these samples have. So this dotted line represents the minimum kinetic energy needed to escape. Escape to where? Well, escape from a liquid to a gas phase. Okay, what we see is that at the lower temperature, okay, so within this region is what we're talking about. Okay, so at the lower temperature, under the blue line, so this little wedge here, we have less molecules, so a smaller fraction of the molecules, a smaller percentage of the sample that has enough energy to break out of the liquid. And if we increase our temperature, now, okay, there's a larger fraction or a higher percentage of the sample that has enough energy to break away and from liquid to a gas. Okay, so notice here that although at the lower temperature, fewer molecules have enough energy to break out of the sample or break from liquid to gas, it isn't completely zero. Okay, so there's some percentage of the sample or some fraction of molecules that's still able to go from liquid to a gas. It's just that as we increase temperature, now we're putting more energy in. Okay, so now a higher percentage of the sample, or a higher fraction of the molecules, have enough energy to break from, or to phase change essentially from liquid to a gas. Okay, but notice it's not zero at any point. Okay, so that'll be important in just a few minutes. So understand that when we increase temperature, we're increasing the average kinetic energy of the sample, and when we do that, we also have a higher percentage of molecules that can phase change from liquid to a gas. Okay, so the higher the temperature, the faster the rate of evaporation, of course. So we know when it rains on a hot day, it evaporates much more quickly than if it rains on a cold day. Okay, so higher temperature, higher rate of evaporation. Okay, and we're going to take now a look at dynamic equilibrium. Okay, so here we have a sample of water inside of a flask, and we have a cork on top. What we'll have is that some of the molecules, so remember, even at low temperature, some molecules have enough energy to escape from a liquid to a gas. So if we were to cork the sample and just leave it be, okay, some of the molecules will make a phase change from liquid to a gas. Okay, and depending on how strong the forces are keeping them in the liquid phase, Okay, we may have more molecules or we may have less molecules. Okay, and simultaneously, as some of the molecules are leaving the liquid phase into the gaseous phase, we have some molecules that will maybe collide with the surface and lose energy. So either with the surface of the flask or maybe with the surface of the water. Either way, they're losing some energy. Okay, and they'll condensate back into the liquid phase. Okay, so we have this coming and going sort of thing happening. So some molecules are entering the gaseous phase and some are leaving. Okay. So if the rate of evaporization is equal to the rate of condensation, we have what's known as dynamic equilibrium. Okay, so this means that the rate of molecules leaving the liquid phase to the gaseous phase is equal to the rate of molecules entering the liquid phase from the gaseous phase. Okay, so at the point when evaporation and condensation are equal, when those two rates are equal, we have dynamic equilibrium. And it's at dynamic equilibrium that we measure vapor pressure. Okay, so vapor pressure is the pressure exerted by the vapor when it's at dynamic equilibrium with its liquid. Okay, so in other words, if we were to have some way of measuring pressure here instead of just having a cork, the amount of force that the liquid is exerting on the surface, or maybe if we had a detector, so on the cork essentially, the amount of force pushing out, that's our vapor pressure. Okay, and we just saw that this is a temperature-dependent quantity. So we know that as we increase the temperature, more of the molecules will have enough energy to exit the liquid phase. Okay, so as the temperature increases, the vapor pressure increases. But notice one very important thing here. So most of the time we said, for most of the properties we've looked at, if we have stronger forces, that gives us a higher property, or a higher degree of that property. In this particular case, if we have weaker attractive forces, that gives us higher vapor pressure. And that's just because if I have less pulling the molecules, or less keeping the molecules in the liquid phase, the easier it is for them to enter the gaseous phase. Okay, so weaker forces give you higher vapor pressure, and higher temperatures give you higher vapor pressure. One is due to kinetics, and the other is just due to the attractive forces themselves. Okay, so if I put more energy in, more of them can escape, and if there's less for them to fight, more of them can escape. Okay, so those both lead to higher vapor pressure. Again, if a substance has a high vapor pressure, this is said to be a volatile substance. Okay, so maybe you've heard the term volatile organic solvent. So these would be solvents that have sort of weak attractive forces that evaporate very easily. Okay, so they have high vapor pressures, in other words. Okay, so here is the vapor pressure curve for water, and this is essentially a phase diagram. Okay, so the important thing to know here is that this blue line represents a phase change between a liquid to a gas. Okay, so we can go ahead and label those. So everything on the left side of the curve will be a liquid. Everything on the right side of the curve will be a gas. Okay, and we have vapor pressure plotted against temperature. Okay, if we just take a look at a couple points here. Okay, so at 100 degrees C, with this particular sample, we have 400 torr of vapor pressure. Okay, if we have at 80 degrees C, we have 600 torr of vapor pressure. Okay, well, suppose we wanted to know maybe where the boiling point of this substance was. Okay, so first we would have to find what's our normal temperature or our normal pressure in our room. So we know that a normal room has a pressure of around 1 atm or 760 torr. So suppose I wanted to know, where does this particular substance typically transfer between a liquid and a gas? Okay, and so I would find my normal room pressure, so 760 torr is 1 atm, follow this line across, and that would bring me to 100 degrees C. So that would be where my sample normally transfers between being a liquid to a gas. In other words, it's my normal boiling point. And at these other points, okay, so if I wanted to know at this pressure, so it's kind of interesting because in this particular instance, I'm essentially equating the vapor pressure to being the pressure of the room. Okay, so remember that in a sample, so if I have just a puddle of liquid, the pressure pushing out is the same as the pressure pushing in. Okay, so that's kind of the analogy I'm drawing here. Okay, so at 760 torr, if we have a 1 atm room, okay, and I come to where my phase changes, that would tell me my normal boiling point. Okay, we could also read this in reverse. So I could say, for instance, what state of matter is this particular substance in at 100 degrees C and 400 torr? Okay, you would say it was in the gaseous state. Or I could say, what state of matter is this in at 80 degrees C but 600 torr? Well, you would say a liquid. Okay, so we're going to get into reading these phase diagrams in just a moment a little bit further. But that's sort of the basics of it. Okay, so this is just one particular instance where we're looking particularly at vapor pressure versus temperature, and we see that phase change between a liquid and a gas. So in speaking about how we measure vapor pressure, so this is sort of what I was talking about. Okay, so we have here liquid ethanol, and so this is before evaporation. So we have what's called a manometer or a monometer, and this is how we measure vapor pressure. So we just take a sample of the liquid, and we close this valve, and we close this valve. Okay, we basically allow the liquid to reach equilibrium. Okay, we can open this valve, and then we can measure the amount of pressure being exerted. Okay, maybe it's a sample of mercury with some gratings on it, or it could be a sample of something else, some heavy. Usually mercury is used because it's heavy, and it doesn't let really air or anything flow through. Okay, so the difference between this point and this point would be the vapor pressure of the gas. Okay, and we would do this at equilibrium. So basically, looking at how much it displaces whatever liquid, usually mercury again, measuring how much it displaces that liquid will tell us the vapor pressure. Okay, I'm not really going to ask you to recreate this or anything like that, but this is a way to understand how we measure this. Okay, so a couple terms here. So boiling point, we know, is when the temperature of a liquid reaches a point where its vapor pressure is the same as the internal pressure. Vapor bubbles can form anywhere in the liquid, not just at the surface. Okay, so this is why, if we go back to our phase diagram here, our vapor pressure curve, that's why I was kind of saying that the force being observed outward by the liquid is sort of equal to the force being pushed back on the liquid. Okay, based on this definition. Okay, so when the temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, that's when we get to boil or start to boil. Okay, so that's why I was saying that at any point in this curve, you can figure out at that pressure and at that temperature what phase it's in, because we're assuming, at least I'm assuming in this particular instance, that this vapor pressure is essentially equal to the room pressure. Okay, so that's kind of what I was getting at there. Okay, and here we can take a look at normal boiling point. Say the normal boiling point is the temperature at which the vapor pressure of a liquid is equal to 1 atm. Okay, so anytime we say normal, we're talking about basically STP, so 1 atm. Okay, so if we take a look at the elevation here, okay, we look at the approximate pressure in atm and the approximate boiling point of water. Okay, so what we notice here is that if we go up in elevation, so we start from the highest, so Mount Everest, here we have approximately 0.32 atm. Okay, so we have lower pressure than if we come all the way down to sea level, or at maybe 20 feet above sea level, we have a pressure of 1 atm. Okay, so our boiling point at high elevation, where we have lower pressure, is lower. Okay, so why would that be? Well, as I said, there would be less pressure pushing back against the liquid. So remember, we're talking about when the vapor pressure is equal to the external pressure. Okay, so if the external pressure is lower, then the boiling point will be lower. Okay, and as we go up in elevation, our pressure becomes lower. Okay, so our boiling point also lowers. Okay, if we're closer to sea level, we have higher pressure, so our boiling point is also higher. So if I was to ask you, where would water have a lower boiling point, on Everest or at sea level, make sure you can answer that question. So one kind of cool technique used in the lab is that you can actually make substances boil at room temperature, okay, by applying a vacuum. So this is a sidearm flask or a filtration flask where we have a stopper, in this case, instead of a filter. You could also use this for filtration. And we have a hose that's attached to vacuum. Okay, so we have a vacuum. So if we remove the pressure, or we lower the pressure inside of the flask, remember, boiling point occurs when the vapor pressure of the liquid is equal to the vapor pressure of its container, or the room, or whatever you want to say, its environment. Okay, so if I lower the pressure of its environment, of the flask, okay, then it's much easier for the vapor pressure to now meet that, or be equal to that pressure, and essentially start to boil. Okay, so if you have a strong enough vacuum, you can actually boil things like water at room temperature. And it's very easy to boil things like volatile solvents at room temperature. And this is a very, very common technique used in chemistry. Okay, so if I have a reaction, I run the reaction, and I want to remove the solvent after the reaction is complete, I can apply a vacuum, remove my solvent, and then be left with my products. And maybe I need to do some filtration or whatever it is after that. But if I want to remove that solvent, then all I have to do is apply a vacuum. Okay, so let's take a look at a couple more vapor pressure curves. So we won't go as in detail with these, but here we're going to compare things with higher vapor pressures with things out with lower vapor pressure. So if we take a look at something like diethyl ether compared to ethyl alcohol compared to water, and then compared to ethylene glycol. So we have vapor pressure on our y, temperature on our x. Okay, and let's look at some information we can get from this. So one thing we can get from this is, for instance, its normal boiling point. So remember, normal we mean at 1 atm, in other words, 760 torr. So if, for instance, we wanted to know which of these substances had the lowest boiling point, we would find 760 torr, and remember that each of these lines indicates a phase change, but for that particular substance. Okay, so what we want to find is, at 760 torr, where do each of these substances go through that phase change? Okay, so for instance, for diethyl ether, we follow this line across and down, we would find that it has a boiling point, a normal boiling point of about 34.6, and we could do that for each substance. Okay, so we could also make an estimation of what phase each of these substances would be in at certain temperatures and certain pressures. We could also compare vapor pressures for each of these liquids, so which is more volatile than the other, which has higher vapor pressure than the other. Okay. And there's a lot of things you can get from this. And notice that all the way down here, ethylene glycol, so even as we really increase the temperature well beyond 100 degrees, still it hasn't really, so its vapor pressure really hasn't increased very much. Okay, so it really takes a very low external pressure to increase the vapor pressure of ethylene glycol a lot, or a very high temperature. So it takes a lot of energy or a very low pressure to get this substance to boil. Okay, compared to something like diethyl ether, or even at high pressures and at low temperatures we boil. Or in other words, you could look at it in terms of even at low temperatures, it has a high vapor pressure. So there's kind of both ways you can look at this. You can either look at this as being, at this point it's equal to the external pressure, or you could say even at this temperature, or at this temperature it has this much vapor pressure. So you can kind of get both of those things from this. Okay, we're going to look at some more phase diagrams at the end and see what other information we can get from these, and we'll see multiple phases put together. But for now, let's just try to answer these questions. Okay, so the first one, it says, which of the following is the most volatile? So there's a legend over here. I know it's probably a little hard to see. Hopefully you can read it. But it wants to know which of these is the most volatile. Okay, so just find the line that you think represents the most volatile compound. Try to find it on this list, and that should be your answer. Okay, so hopefully you said that this line all the way to the left would be the most volatile. And why do I say that? Well, because at the lowest temperatures, it has the highest vapor pressure. So even at 10 degrees C, it has the highest vapor pressure. Okay, or you could say even at 10 degrees C, it changes phases. Okay, so what's our answer? That's the ether line. Okay. So it says which of the following has the strongest intermolecular attractions? Okay, so now we have to remember, okay, so if it has strong attractions, what does that tell me about its vapor pressure? Okay, so if you see if you can come up with the answer for this one. Okay, so hopefully you answered B, which is the blue line all the way here, over here to the right. So how do I know it has the strongest intermolecular attractions? Well, that's because at any given temperature, it has the lowest vapor pressure. So remember, stronger attractions give you lower vapor pressure. Okay, one more. So which of the following has the highest normal boiling point? Okay, see if you can come up with this one. Okay, and this is actually the same answer. So how do we find this out? So we come to around 760 torr, or here we have millimeters of mercury, those are equal. Okay, we come across and we see that who has the highest boiling point? Well, the same line all the way over here to the right. Okay, so that would be our correct answer. Okay, so this last section we'll talk about phase diagrams, and this I think is a topic students tend to like because it's essentially just reading graphs. Let's start out with a kind of a cool idea though first. Okay, so we'll start out with this idea of a supercritical fluid. So what is a supercritical fluid? Okay, so it says as a liquid is heated in a sealed container, more vapor collects, causing the pressure inside the container to rise. So we have a sealed container where we have liquid, a liquid, okay, and we can see the line between the liquid phase and the gas phase. So we have this line. Okay, so what happens if inside this sealed container we increase the temperature? And we increase it so much that the substance actually starts to boil, so we can start to see the bubbles forming. Okay, so we know that there's now molecules escaping the liquid phase into the gaseous phase. Okay, and if we keep increasing the temperature, notice the phase difference between our gas and our liquid really starts to blur at this point. We're not really sure what's a liquid and what's a gas. And if we keep increasing the temperature, now we get to what's called a supercritical fluid. And this is at the temperature and the pressure where the meniscus between the liquid and the vapor disappears, and the states become a single form called a supercritical fluid. So it blurs the line between a gas and a liquid. Okay, so it's not either, but it actually has the properties of both. Okay, so down at the bottom it says supercritical fluids have the properties of both gases and the liquid states, and that's true. One very common example of this is CO2. Okay, and these are used as solvents for very sort of particular reactions where you want to be able to do the reaction in a supercritical fluid, and then when you're done with the reaction, you can just release the pressure, and if you're using something like CO2, then it all just goes back into the gas phase, and you can remove it very easily. Okay, but this is kind of a cool thing. These are actual photos of a supercritical fluid being formed, and usually the chambers are very, very small like this. Okay, you need lots and lots of strength in your container to do something like this. So it's at a very, very high pressure and very, very high temperature. Okay, and the most common uses for this I can think of are to do reactions inside of the solvent, basically. So to use the supercritical fluid as a solvent. Okay, so a couple things. So there's the critical point, so some definitions. And we're going to look at these on an actual plot in just a second. So we have the critical temperature. So this is the temperature required to produce a supercritical fluid. The critical pressure, the pressure at the temperature of the critical fluid, or the pressure at the critical temperature. And the critical point, the combination of the critical temperature and pressure. Okay, so at the critical point, the gas cannot be condensed into a liquid no matter how high the pressure gets. Okay, and we'll look at how to label these. So we're going to take a look at what we call phase diagrams. Okay, so phase diagrams describe the different states and state changes that occur at various temperature and pressure combinations. And we've already kind of looked at these for liquids. Okay, so the regions represent states, and the lines represent the state changes, or in other words, the phase changes. Okay, so we have a liquid-gas line, and it's a vapor pressure curve. Okay, and at that point, both states exist simultaneously. Okay, and then we have the critical point is the furthest point on the vapor pressure curve. And we'll look at these. I'll put pictures to it. I think it makes it a little easier to understand. Another definition is the triple point. So this is the temperature and pressure condition where all three states exist simultaneously. And then for most substances, freezing point increases as pressure increases. Okay, so let's take a look at these on an actual curve. So this is what a phase diagram looks like. Okay, so we have pressure on our y and temperature on our x. So each region, so this would be a region, this would be a region, this would be a region. So each of these regions represents a phase of matter. Okay, so our first region is solid. Okay, so then our blue region would be liquid, and our gray region or tan region would be gas. Okay, and then we see our critical point way out here to the right. Okay, so as we cross this line, we're entering into a different phase. Okay, and so we can see that moving across the line here, we go from a liquid or a solid to a gas, excuse me. So that would be sublimation. Okay, moving across the line here, we go from a solid to a gas. So that would be, or solid to a liquid, excuse me, I'm sorry. So a solid to a liquid. So that would be freezing or melting. So depending on which direction we're moving. Then we have vaporization, so moving from a liquid to a gas. Okay, so, and then there's some points on this curve. So A would be our triple point. Okay, so at A, it exists simultaneously as a solid, a gas, or sorry, a liquid and a gas. So the word vaporization there is throwing me off. Okay, so at that point, it exists simultaneously. So remember, at any point on the curve, it's both of these. Okay. Okay, so notice that this line kind of far out here between the liquid and the gas, that's actually our vapor pressure curve. So that's the segment of this plot that we were looking at before, only dealing with the liquid and the gas. Okay, so that would be the fusion curve, in other words, going from solid to a liquid. Then we have sublimation curve as well. Okay, so we could look at things like what would be the normal melting point, what would be the normal freezing point. Okay, so if we just look at 1 atm, we look at where would it change states. Well, it would change states at this point. So, or if we look at, okay, where it would change states from liquid to a gas, what would be its boiling point? That would be here. Okay, so I can read what phase something would be in, or at what temperature or at what pressure something would change phases based on these plots. Okay, so one thing you want to be able to do is make sure you can label solid, liquid, or a gas. And most phase diagrams look very similarly to this. They don't all have this exact same shape, okay, but generally speaking, you should be able to recognize that at low temperature, low pressure, we have a solid, and then at sort of low temperature, at higher temperatures, lower pressure, we have gas. So these things you should hopefully be able to recognize. Okay. So I could ask you, for instance, what phase of matter is at point A? And you would say that's the triple point, or you would say the correct answer of what phase of matter is there, solid, liquid, and gas, all at the same time. Or at C, what phases of matter do you see? You would say a solid and a gas simultaneously. So those would be your answer. Or I could say, at 1 atm, where does this substance boil? Or where does this substance boil at a lower temperature? Or something like that. Okay. And then all the way out here at B, we have our critical point. Okay, so this is where we have liquid and a gas simultaneously. So anything beyond this point in any direction would be basically a critical fluid, a supercritical fluid. Okay, so let's kind of look at how to use these. Okay, so one thing I could do is I could ask you at a particular pressure, what phase changes occur. So I could ask you, follow this curve from left to right and tell me what phase changes occur in what order. So you could say, okay, it goes from a solid liquid to a gas. Or I could ask you, for instance, what is the normal melting point of this substance? You would find normal pressure and then come across, find where it melts, and then you would say, okay, well, I know that is my normal melting point. Okay, so hopefully you probably will see a kind of a weird cut there. My PowerPoint actually froze on me there. So let me try to say this again. So I could ask you, things like what's the normal boiling point or what's the normal freezing point or melting point, and you would just follow the curve at that particular temperature or pressure, excuse me. So for instance, at 760 torr, we know that's 1 atm, and you would just follow the line across. And you would say, okay, well, I know this melts at this temperature, I know it boils at this temperature. And that's just based on knowing that these lines represent phase changes. Or I could say, maybe down here at 500 torr, is it possible to sublime this substance at any temperature? So you could follow this across and say, well, yeah, I could sublime it at that temperature. Okay. So that's one way we could look at this. Okay, or we could use it like this. So I could say, okay, what phase changes occur if I move, for instance, what phase am I in at 0 degrees C and some pressure? And what happens if I increase temperature? Or if I decrease temperature? Okay, so now I go into a gas. Okay, so I'm lowering my pressure. I'm sorry, if I lower my pressure, not lower my temperature. So at that temperature, what if I lower my pressure? So I'm getting a little flustered from the freezing. So if I, for instance, if I lower my pressure at this particular temperature, what happens to my phase? So, okay, now I go back into a gas. Okay, or then, okay, so what phase change occurs if I increase my pressure? Okay, well, then I go back into a liquid. Okay, so that's how you sort of read these. So you can either follow them based on a single pressure or follow them based on a single temperature. Okay, so sort of an interesting experiment here. If you are to take a solid block of ice and hang 2 weights off of it in this way, what do you think will happen? So what are we doing? So we're keeping the temperature the same, but we're increasing the pressure. So if we come back to here, so keeping the temperature the same, so at 0 degrees C, but we're increasing the pressure, so we're increasing pressure, what will happen? Okay, so we're at this point, somewhere in here. Okay, but we're increasing the pressure, so we're going to go from a solid to a liquid. Okay, so here, if the weights increase the pressure, what will happen? Okay, well, actually what happens is it starts to melt, and eventually the wire will actually cut all the way through. Again, because if we're at some particular pressure and temperature, if we increase our pressure, we'll actually move into being a liquid. So we'll actually start to melt the ice. So kind of a cool experiment. Okay, so here's our phase diagram for CO2. Okay, so CO2, if we freeze it, this is what we call dry ice. Okay, so at 1 atm, notice it has a sublimation temperature, not actually a boiling point, but a sublimation temperature. So that happens first, actually, of minus 78.5 degrees C. So it's very, very cold. Okay, so this is why as dry ice heats up in your cooler, maybe if you're transporting something a long distance, you're not left with any liquid behind. So it actually sublimes on you. So it actually at normal pressure, it's actually more likely to sublime. So in order to get it to actually go into a liquid, we need a lot more pressure. Okay, so remember our supercritical fluid? What do we need? We need high temperature, high pressure. So at normal pressure, CO2 actually goes from being a solid into a gas rather than going from a solid to a liquid. Okay, so let's try to answer this question. So it says, consider the phase diagram of CO2. What phases is or are present at each of the following conditions? Okay, so we have a few different phases here. So let's just go through this together. So first at 20 degrees C and 72 atm. So we're at 20 degrees C and then 72.9 atm. Okay, so we'll come up here. So what phase are we in? See? So we're in a liquid. Okay, the next one. So minus 56.7 degrees C and 5.1 atm. So to answer this, you would, find 56.7, come up to 5.1 atm. Oh, and that happens to be at the triple point. Okay, so what phase are we in at the triple point? So don't get this one wrong by saying we're at the triple point. If I asked you what the point should be labeled or what the point was called, that would be your answer. But if I ask what phase is there, well, that would be solid, liquid, and a gas. And those are all simultaneous. So that's our triple point. Okay, next one, 10 degrees C and 1 atm. So at 1 atm, and then say 10 degrees C is maybe here. Okay, so what phase are we in? Okay, so we're in a gas. Okay, so that's one more. So minus 78.5 degrees C and 1 atm. Okay, so at 1 atm and at 78.5, or minus 78.5. Okay, so what phase are we in? We're in both a solid and a gas. Okay, so if we're on the line, remember, if you're on the line, you're in both states. If you're somewhere nowhere near a line, then that's the state you're in. Okay, but if you're actually on the line, okay, you're in both states at once. So 50 degrees C, 80 atm. So way out here and way up here. Okay, that's going to be our critical point. So what state are we in? We're in a supercritical fluid. Okay, so here it wants us to consider the generic phase diagram, what phases is or are present at the points A through G. Okay, so see if you can label this. So no, absolutely nothing is labeled, no temperatures, no pressure. See if you can go in and label this. So pause me and see if you can label this, and we'll go into it together. Okay, so hopefully you were able to answer all of these. So let's try to label this at A. So what phase would be at A? So we haven't crossed any phase boundaries. Okay, so what point should we be at A? Well, we should be in a solid. Okay, so we're always going to start from a solid in this region. Okay, so if we haven't crossed any phase boundaries, and then we must be in a solid. Okay, next one, B. So we've crossed a phase boundary at, so we've crossed a phase boundary here. Okay, so what phase could we be in? So we're at relatively high temperature, pretty close to normal pressure. What should we be in? That should be a liquid. Okay, then at C, we've crossed this phase boundary without entering this one up here. Okay, so what phase are we in there? We're in a gas, of course. Next one, D. So sometimes you'll see the critical region labeled like this with two phase boundaries like that. It doesn't have to be. Okay, but just know you're crossing from the liquid phase boundary and the gas phase boundary. So what should that be? Of course, that's supercritical fluid. E. So E, we're on the line between solid and a liquid. So we would put solid and liquid. F, we're on the line between liquid and gas. So we would put both of those. And then finally G, we're at the triple point. Okay, so that would be solid, liquid, and a gas. Okay, so that will wrap it up for this chapter. Hopefully that wasn't too terrible. All right, I will see you in the next one.